right? We have already discussed about the, linearly dependent and linearly independent set in our last class. We'll just quickly review that concept. I would like you to read that definition. So the definition that we discuss in section, in chapter 1 is that linearly independent means an index set of vectors, v sub 1, v sub 2 up to v sub p, and v is said to be linearly independent if the vector equation c1 v1, c2 v2, cp vp equal to 0. So that's just a linear combination of all these vectors. C1, C2, C sub 1, C sub 2, and C sub p represent the scalar. We call it weights. And if this equation has only the trivial solution, what it means is only if each of the, in order for this equation to be 0, if each of these constant, each of these scalar are individually 0, then we call it linearly independent set. And then if this equation is 0 without being all of this scalar individually 0, then we call them linearly dependent set. And then we learn many different methods of, working method in order to check whether the given sets are linearly dependent or independent. When we are given a vector that contains 0 vector, then this is obviously a linearly dependent set. We discussed that. And a set of 2 vectors is linearly dependent if and only if one is the multiple of the other. So these are the things coming from section 7.1. Okay. Example 1. I want you to tell me part A. Is this linearly dependent or independent? Part A. Either you can, sorry guys, this one is just, where did it go? Part A, linearly dependent or independent. You can write either in the chat room or you can tell me using your microphone. Sometimes I'll call your name as well.
It's dependent sets because it contains 0 vector, 0
Excellent.
set.
Excellent. Okay, yes, because it contains 0 vector. Okay. Now remember, in this matrix also we consider this as a vector because we have proved that these are the objects in the vector space, and matrix 2 by 2 is a vector space. We have already proved that. Good. Part B, what do you think? Is that linearly dependent or independent?
It's independent.
Why?
Because the 4 is no multiple of 3.
Excellent.
No, 11. 11, no multiple of 3 times 4.
Yes. Because when there are 2 vectors, then it's pretty easy to check, right? We just check whether one is the multiple of the other or not. So this one is linearly dependent. This is linearly independent because you already told me the reason, because not multiple of each other, right? This one is not the, it looks like, when you look at that, 1 times 3, good, 2 times 3 is 6, 3 times 3 is 9, but this guy right here, it just violates that multiplication thing. So they are not multiple of each other, linearly independent. Now, here is the theorem. An index set v sub 1, v sub 2 up to v sub p of 2 or more vectors with v1 is not equal to 0 is linearly dependent if and only if some v sub z is a linear combination of the preceding vectors v1, v2 up to vz. Okay, that's the theorem. I want you to remember. So example 2, I think we have done very similar questions before in section 1.7. Can you recall this section, recall from section 1.7 and try to figure out whether this set is a linearly dependent set. So one method is that what we can do is this C1 P1 of t plus C2 P2 of t plus C3 P3 of t equal to 0, and then we work it out that way. But there is a even easier method in order to solve this. Now the question is, you see here P3, can I write, this is what we did in section 1.7, but here I want to do using this theorem, the theorem number 4. What that theorem tells us is that if some Vj, some vector can be expressed as a linear combination of the other vectors, then the set is linearly dependent. Now my question is, this P3T, can I write this as a linear combination of P1 and P2? P3T is essentially 4 P1T plus 2 P2T. Is that right?
Yes, sir.
This is your V1, this is your V2, and this is your V3. Now what I can do is I can write V3 equals as a combination of the previous two. So 4V1 plus 2V2. So if I can write that way, then the set is linearly dependent. So this one is P1, P2, P3 is linearly dependent set using theorem 4. Okay, theorem 4 is telling all about this. If you can express some of the vectors as a linear combination of the other, then the set is linearly dependent. Now you don't have to do all of these now. You don't have to solve that system of equation. That's what we learn in section 1.7. If you want to do it, no problem. Okay, you can still use that. But if you somehow can show that one vector is a linear combination of the other, then it saves time. It's a shortcut. That's the idea. Example 3. Are these vectors linearly independent? Okay. If we want to show that these vectors are linearly dependent or independent, the thing is, what we do is we consider this. Let's say this is my V1, V2, V3. And using that theorem 4 is kind of difficult in this case. The easiest method would be, we consider the linear combination C1V1 plus C2V2 plus C3V3 equals 0, which means this. And now this is a system of, we can consider that as a system of equation. It's a vector equation, right? Okay, so you consider the augmented matrix or maybe coefficient matrix, it doesn't matter. Change it into echelon form. That's what we did. If we change this into echelon form, then how can we check whether the system has, whether these vectors are linearly dependent or independent? Let's say I have this vector 1, minus 1, 2, 3, minus 2, 3, 1, minus 2. Is that minus 2? Yeah, minus 2. And 1, 0, 7, 7. Okay, suppose I change this into echelon form. Then what? How can I check whether the vectors are linearly dependent or independent? Can you tell me, either in the microphone or? You can consider, if you want, you can consider this augmented matrix. It's not required, but you can consider that as well if you like.
Can we solve it and check if it has free variable and no or no free variable?
Exactly. Okay. So let me change this into echelon form. This is what I got. Okay. So we are doing this example 3. Now, is there any free variable?
Yes, x3 or
X3. Okay. X3 is free. So linearly dependent. If there is a free variable, linearly dependent. That's what we discussed, right? Free variable, linearly dependent. No free variable. Again, this system consistent. That's one of the condition. Consistent and free variable, linearly dependent. Consistent but no free variable, linearly independent. So that's what we learned in chapter 1. And in chapter 4 we learn another technique, that whether we can actually express one vector in terms of the other one. If we can do that way, then they are linearly dependent. That's another method that we learn. Okay. Now let's try example 4. I don't know, we have done that in section 7.1. I think we have done similar question. Do you want to try this? Let me suppose that as V1, V2, V3. So now consider a linear combination C1, V1 plus C2, V2 plus C3, V3 equal to 0. Right? In order to check that, we create that vector equation and then we consider the augmented matrix or coefficient matrix, change it into echelon form. That's what we're going to do. But in case of matrix, let's see how we can do. So this means, can I write C1, 0, 2, C1, 5, C1 plus 3, C2, 4, C2. We can add all of them. Okay, the component wise, the first component, first row, first column component element here, C1 plus 3C2 plus 0. We add them all. Second one is 0 plus 4C2 plus 0. This one is 2C1 minus C2 plus C3. This guy is 5C1 plus 6C2 plus C3 equal 0 can be written as 0, 0, 0, 0. Now what does that mean? We can actually write down this as C1 plus 3C2 equal to 0 because this component and this one must be 0 and another is 4C2 equal to 0 Another is 2C1 minus C2 plus C3 equal to 0. 5C1 plus 6C2 C3 equal to 0. Now we have this 4 equation. Either you can change it, now the goal is to solve this system, okay? Solving this system. Either you can use augmented matrix, or I think the easiest one would be, you can use the high school method also if you like. Can you tell me what are the values solving this system? What do you get? C1 is what? C2 is what? C3 is what? Let me know.
C1 0, C2 0, C3 0.
I want to check with other people if you get the same thing.
Yes.
Okay, so what does that mean? Is the system linearly consistent or, linearly dependent or independent?
Dependent. Independent.
Okay, now that's why the definition is important, right? Let us go back to the definition, what linear independent is. So we are not using any theorem here. We're just trying to use the, I think, definition. And the definition says, we consider that equation, vector equation, right? Which is homogeneous equation actually, has only the trivial solution. That means all these values are individually 0, then we call it linearly independent. So that's by definition. Okay, so by definition, because these are only trivial solution, by definition, the given set is linearly independent. All right. Okay, it's a quick review from section 1.7, and then now we will discuss a new concept. Is there any questions so far, guys? It's just a quick review from this previous chapter, and we'll continue this in the later class as well. Now, one of the main concept that we'll be talking about before the break is this basis. And we'll be talking about basis and linearly dependent and independent throughout this course. You need to have a really good understanding of this, guys, okay? If you have any questions, if you have any confusion, please let me know. Because every other concept will be based on this idea of linearly dependent, independent, and basis. Okay, first, please read the definition. Let H be a subspace of a vector space V. An index set of vectors in V is a basis for H if it satisfies these two conditions. First condition, B must be linearly independent. Okay, all these vectors B1, B2 up to B sub P, this set must be linearly independent. And the subspace spanned by B coincides with H. That is, H must be the span of that. What does that mean? Span means, recall from chapter 1, span means we can write these as some linear combination of those vectors. So that means we can write this as C1, B1 plus C2, B2 plus Cn, Bn, or CPBP. We should be able to write this in that form. That's the meaning of a span. Okay, so this guy right here, we call this, we can write the whole thing linear combination as a span of that. So two conditions it has to satisfy. Condition 1, the set must be linearly independent. Condition 2, then those set must span, means must generate or must create that space H. All right, and there is a note. I want you to keep the note, okay? Keep in mind, a basis set is an efficient spanning set containing no unnecessary vectors. No unnecessary vectors. Okay, what it means is in day-to-day life, I think this is not a mathematical example. You can relate that concept with this one, okay? Once again, it's just an idea to remember. Suppose when I say water, what does that mean? It must have S2NO, right? It must be that. But if I say water, the water that we drink, it has not only H2O, it has some, maybe, you know, some other minerals. Maybe it may have some copper, it may have some, you know, some magnesium you can put, some other, you know, it can have iron, it can have salt. Okay, so those, they are also called water, right? If you can mix all of them, like the water, the drinking water that we have, it has so many minerals, right, in it. But even if we delete those minerals and if we just have H2O, then this is still water. So that means basis for water is this. That is the efficient. There is no unnecessary element. But these other elements are unnecessary for this to be water. You can add it, no problem. But the essential part of the water is this. And that is, you can consider as basis of water is this. You can say that. Again, this is not a mathematical, really nice example, but it's just an analogy that some people find it easy to remember. So most efficient vector. Okay, in order for this to be a basis, there should be no unnecessary vector, no unnecessary element in that space, in that set. Let's look at that example 5. Now the mathematical way of looking at it. Let S be a plane illustrated below. So here is the plane. Notice that this one is your V1, this is your V2, and this one is your V3. V1 and V2 and V3 lie on the same line. Just keep that in mind, same direction. Okay. Which of the following is valid description of H? Which are the basis for H and Y? My question to you is that H means this plane, okay, that, you know, this plane that you can see. Can I create that plane if I'm given only two vectors, V1 and V2? If I am given these two vectors, can I create that space? Can I express every single point in this plane using that V1 and V2? Yes or no? Can I express this point just using V1 and V2? Can I ignore V3 at this point? Yes, okay, good. Because I can write that point as V1 plus V2. This point also I can express using V1 and V2. This point I can also express as V1 and V2. That will be V1 plus 0 V2. This point, yes. This point, yes. Every single point, yes. So this is the, you know, we can generate H using V1 and V2. That is the valid description. Part A is good. How about part B? if I'm given v1 on that direction and v3 on that direction, can I create every single point on this for this plane? Yes or no? Suppose I'm, this v2 is not given. I'm just given v1 and v3. So can I generate this plane? In another word, can I express this point using v1 and v3? Yes, okay. Can I express this point in terms of v1 and v3? Yes. This one, yes. This one, yes. This one, every point can be expressed using this. So this is part B is also the valid description. Let's say part C. Part C, I'm given only v2 and v3. Can you express this point using v1, v2 and v3 only? This v2 and v3. Can I express that point?
No.
Yes or no? I have a vector only in one direction. You cannot go. Okay, yes, no. We cannot express that point using v2 and v3. We cannot express this point using v1, v2 and v3. Okay, they are just on the same direction. Basically, this is only one vector, right? It's just a multiple of the other one. So no. So C cannot be. How about this? If I'm given all these three vectors, then yes, I can generate the whole thing, right? Now, D is also okay. Now, what is the basis then? We don't need any unnecessary vector. In this case, v1 and v2, can it be basis? Are they necessary vector? Yes, they are necessary, right? How about v1 and v3? Yes, they are necessary because v1 and v3 can be the basis. And how about v1, v2, v3? There is one extra vector, so this cannot be the basis. Okay, there is one unnecessary vector. Either you can remove v2 or you can remove v3, but there is more than required vectors. So that is not the basis. So basis means only these two set. This is all about basis. Do you have any question so far? So if you understand this question, this example 5, you have a good idea about what the basis means. It includes only the essential vector, necessary vector. If there is any unnecessary vector, even though v1, v2, v3 is a valid description, you can create that, but there is one unnecessary vector, so you need to remove that. Either you can remove v2 or v3 in order for this to be basis. Okay. Now we will learn, every time checking this way is it requires a lot of time and energy. So what we do is we will now learn an efficient method of checking whether the set is a basis or not. Okay, let's look at example 6 and example 7 are similar. Example 8, 9, all are similar actually. Let me do example 7. So definition, remember, definition means linearly independent for basis definition. Linearly independent, and second, span. Two things. Example 7. Now I want you to check whether these vectors are linearly dependent or independent, okay? Weights or scalar, we consider that, which means C1 now consider the augmented matrix. Change to echelon form, please. And let me know. Again, echelon form is not unique, so you may have a different values there, but that's okay. Now the question is whether there is any linear, any free variable or not. Since there is no free variable, V1, V2, V3 linearly independent. Okay, condition 1 is done. Check two conditions. Condition 1 is so condition 1, what we check is linearly independency. Whether the vectors are linearly independent or not, we check that this is linearly independent, so checks the first condition. Condition 2. Clearly, this V1, V2, V3 all in R3 and are linearly independent. So R3 is actually a span of V1, V2, V3. So because they are linearly independent, for R3, it is 3 dimension. You need three different vectors, three different directions to go. Okay, R3, so 3 dimensions. So you need 3 different vectors, 3 different directions in order to create this R3. So yes, of course, V1, V2, V3 are linearly independent, means they represent a different 3 different directions, and so this is span. So it also checks. Therefore, V1, V2, V3 is a basis for R3. Any question, guys, so far? We check 2 conditions, whether it is the span or not, and then whether it is actually the, the given vectors are linearly independent or not. Okay, can we move forward? Can we try maybe example 8 or 9? We'll do one together and you'll do the other one. So which one you want to try? Okay, let's do one questions together. Example 8 or 9. I'll do one and you'll do the other one. Let's take a turn. Which one you want me to try? Okay, Dhruv, you want me to do 9 or you want to do 9?
You.
Okay, me 9. Okay. Everyone is okay with that? So I didn't get a response, so I assume that everyone agree with Dhruv. So let me copy that example 9. Given S equals Pn represent polynomial of degree n. So this means polynomial of degree n. So we need to check 2 conditions. Condition 1, linearly independent. Let's check that. I will consider this as a vector. Maybe I can write this as v1, v2, v3 up to vn. Okay, so consider the equation c1 v1 plus c2 v2 which means where c1, c2 up to cn belongs to R. They are scalar, okay? They are scalar, they are weights, whatever you call it, you can simply write they belongs to R. So then C1 V1 is 1 plus C2 B2 is T plus C3 V3 is T square plus it goes like that plus Cn Tn equal to 0. Is that okay? Now, can I write this 0 as a, can 0 be expressed as a polynomial of degree n? So 0 can be written as 0 times 1 plus 0 times t plus 0 times t square plus 0 times Tn. Is that true? What it means is we can express 0 as a, polynomial of degree n. Now you can actually compare the coefficient. Because in this case, changing into echelon form and then checking whether vectors are linearly dependent and independent, that's a little bit tedious, but I think this method is the easiest one. So I'm gonna use the definition of linearly independent vectors. So comparing coefficient, both sides, what I can say is that, 1 and 1 equal, so C1 equal to 0, T and T here same, the coefficient is 0 and C2 must be equal. T square here, C3 must be 0. It goes like that, so Cn must be 0. So by definition, this 1 T square Tn is linearly independent. So the first condition checks. Now now we need to show that it spans. Obviously, Pn is actually the span of 1 T square Tn. This is pretty obvious. It doesn't require any proof. Because in order for this Pn, then we already know that that's gonna be, A naught, let's say 1 plus A1 T plus A2 T square plus, that is the polynomial. So that means these are the things which are the essential element in order to create Pn. So that is pretty obvious. It doesn't require any proof. Okay, so this clearly spans this one. So spanning is also done. So you can write S is a basis for Pn. Done. Any question? Now I would like you to try this example 8 on your own so that the set is a basis for this one. Example 8, I want you to try so that So M2 by 2 means it represents the matrix of size 2 by 2, all possible matrix of this 2 by 2 size. Okay, now I want you to try this. Take a couple of minutes, check two conditions. Condition 1 is linearly independent and condition 2 is spanning. Okay, take a few minutes. Okay, let S be the set of vectors in V and H is the span of this vectors. Now, if one of the vectors in S, say B sub k, is a linear combination of the remaining vectors in S, then the set formed by S by removing B sub k still spans H. And if H not equal to 0 for some subset of S, is a basis for H. And this is the theorem that we'll be using. Maybe what we can do is we will solve one or two examples using this theorem, and once we understand what it means, then we'll see the proof later. Okay, let's look at first example here, example 11. B1, V2, V3 is given so that span of this equals span of this, span of set of vectors B1, B2, B3 equals span of the vectors B1 and B2. Note that this is given. Example 11 and 12 are similar. Maybe let's do example 11 first. All right. Then what we can do here is that I'll do this example 11 here. Given V3, okay, let me just write, consider the equations. Okay, first consider equation C1 V1 plus C2 V2 plus C3 V3 equal to 0, where C1, C2, C3 are scalar. Now, given V3 is 2V1 plus 3V2, this is given. So this equation becomes C1V1 plus C2V2 plus C3 V3 means we can substitute the value. So 2V1 plus 3V2 equal to 0. Okay, we can write that. Now, if you simplify this, what you can write is C1 plus 2C3 B1 plus C2 plus 3C3 V2 equal to 0. Right? Because remember, span means, let's say, span of B1, V2, B3, that means this. So this one and this one is the same thing. This means this. Okay, span of B1, B2, B3 equals, even you don't have to write that. You can go directly from here to here. I think that will be even easier for you. So span of this means this. And now given this, substitute the value, you're going to get that. What this means is, this means actually a span of now V1 and V2. There is no more V3. So this equals a span of V1 and V2. So what we have proved is that we started with a span of V1, V2, V3, and we end up with a span of V1 and V2. So what we can say is that hence a span of V1, V2, V3 equals a span of V1 and V2. Is there any question? And that's what we need to prove. If there is no questions, you may want to try this example 12 just for fun. It's the same idea. Example 12, I would like you to try, and then we take a break. In this example, H is the span of this one. So if I take any object in H, that can be written as a linear combination of those vectors by definition. Substituting this value, then what do you get? Okay. Part A is done. Part B, find a basis for the subspace H. Can you tell me, guys, what is the basis for subspace S? Basis for H is so what are the vectors, essential vectors? What are the necessary vectors in order to form H?
V1, V2.
Yes, so V1 and V2. So that forms the basis for H. That's it. Okay, because V1, V2, V3 is actually the same as V1 and V2. So there is one unnecessary vector in this set. In the first set, there is one unnecessary vector, which is actually V3. So basis for H is this one. Done. Okay, guys, let's take 10-minute break. This is the main concept for this section, by the way, basis. We have just done, okay, just based on that examples. So what this theorem 5 tells us is that we have a set of vectors in V, and H is the span of all these vectors V1 up to, BP. So if one of the vectors in S, say Vk, is a linear combination of the remaining vectors in S, then the set formed from S by removing Vk still spans H. That's what we have seen in the example. We are given 3 vectors, and then we prove that even if we ignore that V3, we can still span the given space, right? So, and here is the proof. Let us say that without loss of generality, VP is a linear combination of all of these. Okay, one of the vector is a linear combination of the other one, all the other one. So what we can write is BP is, this will be BP minus 1. So we can write B sub P can be written as a linear combination of all the other vectors up to B sub P minus 1. For some scalar A1, A sub 1, A sub 2, and A sub n. Suppose that X is in H. Then we can write X as a linear combination of all of these vectors from here. So X can be written as all of these vectors. Okay, because we know that this BP is this one, we substitute this VP sub P right here. We replace that, we substitute that value by this one, so that we can write the same X as C1B1, C2V2 up to CP minus 1, BP minus 1, but this V sub P is actually can be written as a linear combination of the other one. Okay, so what we have left with is this BP is gone. Now we have the linear combination of B sub 1, B sub 2 up to B sub P minus 1. Therefore, span of what we have proved here is that span of V1, V2 up to BP is actually the span of V1, V2 up to BP minus 1. We have proved that this one and this one are equal because BP is actually the linear combination of the other one. So we can write this way. That's what we have to prove in part A. And if S is linearly independent, and we are done. So if these vectors are linearly independent, we are done. Suppose among these vectors, if BP minus 1 is a linear combination of the previous one, we can repeat the same process and we can show that this one is actually the span of B1, V2 up to BP minus 2. Okay, we can show that. And if these vectors are linearly independent, we are done. If this guy is a linear combination of the other one, we can repeat that same process. So same thing here. If not, one vector can be written as a linear combination of the others and can be deleted. Repeating this procedure until the set is linearly independent. If at least one vector, which is not 0, remains, then the set is linearly independent and is thus a basis of H. This is exactly what we did in this example 11 and example 12. Okay, now another theorem. The pivot column of a matrix A form a basis of column A. Okay guys, you need to memorize this theorem, okay? We'll be using this later to solve. Pivot column. If you are asked to find the basis for the column space, what you do is you change that matrix into echelon form and figure out what are the pivot column, and that pivot column actually forms the basis for column A. We don't have to check those two conditions. Here is the nice theorem. Let's look at this example, example 13. So we are given a matrix. Now please change this into echelon form. That's the first thing you need to do. Good news is that I think it is already in echelon form, right? Already in echelon form. So what are the pivot column? Okay, let us look at pivot. This one is pivot, meaning basic variable we are looking for, okay? So this one is basic variable, pivot. And this one is another pivot. And this one is another pivot. They are the basic variable. So pivot columns are column 1, column 3, and column 1, 2, 3, 4, 5. These are the pivot columns. So basis for column space of A is actually, just consider that vectors 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. So these are the basis for column space of A. Now, according to the definition, what we have said is that in order for this to be basis, the vector must be linearly independent, as well as this will span the given space. Now, this theorem tells us that pivot column forms the basis for column A. Now, these are automatically linearly independent, guys, okay? When you do this way, these vectors are automatically linearly independent and it will span the column space. It will satisfy two conditions automatically. These vectors, linearly independent, you can actually check by yourself, and it actually span of column space of A. Span of B1, B2, B3. It will automatically satisfy both of these conditions. Okay, so from now onwards, what we do if we want to find the column space, or column space of B, not A, sorry. Column space of B. Just change it into echelon form and go back to the pivot column. Let's look at this example 14. So given A is 3, 6, 6, 12. This is a coefficient matrix, okay? Now find a basis for the null space of A. We'll do that later. Find the basis for the column space of A. We'll do this first. Part B first. Okay, first you need to change it into echelon form. Because our goal is to check what is the, pivot column. Okay, guys, I want you to change this into echelon form and let me know. Am I right?
Yes, I got the same.
You got the same thing, okay. Now my question to you is this, what are the pivot column? One, this is your pivot, and this is your pivot, 1 and 3, right? So column space of A actually is the span of column 1 and column 3 of A. Now you need to go back to the original matrix, by the way, keep that in mind, okay? So pivot column is 1 and 3. So the column space of A is the span of column space of column of 1 and column of 3 from the original matrix, not from the echelon form. Keep that in mind. When I give these questions in the exam, people sometimes consider the columns from this one, from the echelon form. No, you need to go back. So first column means this one and this one. So your column space of A is actually 3 and 6 and 6 and 13. Done.
So from the previous example, we used the echelon form because it was already like that, right?
Yes, because in this example, it is already, the original one already in echelon form. So,
Okay.
right? But here,
Okay, so we must use always the original matrix.
yeah, always the original matrix for column space.
Okay.
And this is one of the thing that I, constantly get, some of the students during the exam, I think some anxiety, some stress, they forget to go back to the original one. They just copy and write it down. So please don't do that mistake, okay? You need to go back to the original matrix for column space. Okay, any questions so far? Now for the column space. Now part A, null space. Okay, part B, we need to find part B. We started first part B for column space. Now part A, we will look at null space. Now recall the definition of null space. Null space means we need to solve AX. If X is in the space, then AX equals 0, right? X is in null space of A. What does that mean? That X is in null space of A, that means AX equals 0. I'll write it here, I need more space. That means AX equals 0. We know that. Now we need to solve this system. Solve this system. So I think the solving this system, the easiest method would be considering the augmented matrix, right? So consider everyone is okay with that. Null space means, when you multiply that, that gives you 0. That's what we call null space. That's how we define the object in the null space. So consider the augmented matrix. Our whole goal is to solve this system. So you consider A and 0. And that means A means what is A? 3, 3, 6, 6, 12, 6, 13, 3, 0, and 9, 3, 0, 0. Now change into echelon form. The good news is that we have already changed it into echelon form, which is 3 and 0. We just copy that from the previous part. 6, 0, 6 and 1, 3 and minus 6, 9 and negative 15. Now write the general solution. So general solution will be, this is x1, x2, x3, x4, x5. So we have 3x1 guys, can I do this? Can I simply write, this? I can take 3 common so that I can get all this 1, 2, 2, 1, 3, 0. Can I write that?
Yeah, I did that. It's just easier.
Yeah, that's easier to calculate later on. So let's do
Yeah.
that. And here also, I think we can write down this as taking 2 common. So, I mean 3 common. So you're going to get minus 2 and minus 5 maybe. Minus 2 and minus 5. That will make Life easy? Oh no. Oh, there is 3. No, we can't write that down. This is -6, -15. Okay, that's good. So the second one is x3 minus 6x4 minus 15x5 equal to 0. And what are the free variable? x2, x4, x5 are free. Okay, now we must express basic variable in terms of free variable, which means x3 will be 6x4 plus 15x5, and then this guy will be x1 plus 2x2 plus 2x3 means 6x4 plus 15x5 plus x4 plus 3x5 equal to 0. Now, can you please solve me and let me know what do you get solving this? So you're going to get x1 equals what? x3, we already have that, which is 6x4 plus 15x5. Now, if you simplify that, what do you get? x1 equals? Parnit, can you tell me what is this? x1 equals how much? Is Parnit here? Dhruv, can you tell me what is this?
We're having negative 13x4.
Same, we got negative 13x4.
And then negative 33x5.
And minus 3x5. Sorry, I got them.
Yeah, it's same.
Okay, good. Okay, then we can write down this as x can be written as x1, x2, x3, x4, x5, which can be written as minus 2x2. This is going to be 6x4. I mean, x2 is free, so we just write x2 as it is. x3 is 6x4 plus 15x4. And x4 is free and x5 is free. Now this can be written as x2 plus x4 plus x5. Let me write it down. x2 means it will be negative 2, 1, 0, 0, 0. This is minus 13, 0, 6, 1, 0. This will be minus 33, 0, 0, 0, 1. Any question? So let me denote this by, this is, let's say this is my V1, this is my V2, and this is my V3, okay? So in part A, let me go back to the question, what we are supposed to do. I just want to see the language. Part A, find the basis for the knowledge space of A. Okay, so the basis for the knowledge space of A is actually these vectors. Okay, like this. Therefore, basis for knowledge space of A is the set of vectors v1, v2, v3. These are the two vectors, I mean three vectors. That is the basis. That's how we calculate the basis for knowledge space. Now, you can easily prove that they are linearly independent and they span the knowledge space. Okay, they are automatically linearly independent and span the knowledge space. So they are the basis for the knowledge space. That's how we calculate the basis. Any question, guys, here? So you learn how to find the knowledge space, how to find the column space, and that's it for this section. What is that section? This 4.3. I think we are done. There is one question. It's the same. So there is no other questions. Anyway, I think we are done with this section. Now, I want to quickly take attendance at this moment to make sure that people are here. And just give me 1 second. So if you have any question, please let me know. Otherwise,